Hey everyone. All right, so I'm going to talk about how Blaze is used in the wild for doing some munging on the taxi trip dataset, and also something I've been working on sort of outside of. It's a Blaze backend. Okay, so here we go. So just a recap of Matt Rockland's talk. Blaze is good at separating computation from data, migrating between different data sources, which he didn't talk about a lot. Yeah, so we'll see a couple examples of that, and providing like a comfortable API that fits in your head, and sort of in the manner of pandas. Okay, so just a couple examples. Okay, so we're taking a couple of Blaze symbols here, creating a data frame, and then computing the sum of a column. Okay, and I'm inputting let's see what else is. Okay. So we have the sum over a data frame column, the sum over the same thing, but I convert it to a list. And then do the same thing on our NumPy record array. Okay? And then there's also this API that Blaze has called into, which is a function that takes as inputs two things and converts one thing into the other. So here I'm converting a data frame to a list, same data frame to a NumPy a record array, and then actually it does something else, which it will put a data frame or one of the other types that we support into some database. Here I chose SQLite because it's the only URL that I can remember. Okay, so you can do that, and drop is another function that's dispatched on a bunch of different types, and it will essentially just drop the table from the database, similar to a SQL drop. And then here I'm just showing that you can chain them, right? So I take the data frame, put it in a database, and then I get it out. Okay, and so yeah, so there's that. And then another thing that is kind of nice about Blaze is that the tab completion is dispatched on the D shape, which is essentially the data type, along with some information about the size of the object. It will dispatch on that to give you the available properties and methods. So for example, here I say d.amount.tab, and I get back some things that are valid on collections of integers. Okay, and then the next line I do the same thing on a string column, and I get back a smaller set of things which are only compatible on strings. So when you're using NumPy, for example, no matter what your column consists of, you'll always get the same API. You won't get a sort of custom tailored to the type of the object. It's kind of nice when you're interacting with things. Okay, so that's that. So as Matt mentioned, Blaze also lets you do it yourself. So if you have a backend, something you're just interested in, you want to create a backend for Blaze, it's pretty easy. Oops, that's not what I want to do. Who's heard of Q? 3, 4, 5, 6. Okay, so that's more than I expected. I expected like maybe 1 or 2. Q is a language heavily used in finance, and here's a couple of examples of like canonical Q. I don't know what you want to call it that, but it's interesting, right? So it kind of looks like you took something and ran a minifier on it and then called it code. So what's kind of interesting is that the way to print something as standard out is by putting a -1 in front of the thing you want to print. Okay? Or that's only if you want a new line at the end. If you don't want a new line, you put +1. So yeah. So 1 divided by cat works in Q. And actually division is the %sign, but whatever. I mean, and so yeah, how about no? So KDB.Py is something I wrote that is a Blaze backend that essentially generates Q code for you. So you can write down a Python expression, and we'll give you. You don't ever have to touch Q except when you're basically setting up your database. Okay, so I don't know if Blaze can do that. Probably not. But let's say somebody hands you a Q database. You go to some hedge fund, and they're like, "Oh yeah, we're using Q," and you're like, "Okay, I want to use Blaze or something." You can do that. Okay, so. The main reason is because this is a ubiquitous thing in finance, but it also is a very, very fast column store. It sort of makes big things feel small and huge things feel reasonably doable. Okay, so it's not just a column store. There's some details around how you structure your database, but I'm not going to go into that. But just if you want to read up about it, just look up Q on Google. So what is KDB-Py? KDB-Py is a backend for Blaze. It generates Q code from Python code, and then that code is run in a Q interpreter, which is sitting in a subprocess. And then actually it's sent over a socket. Q is in a subprocess listening on a socket, and you send to the socket, you read back from the socket, and you get back Python things, which is kind of nice. So I'll show you an example. So I have a notebook somewhere, not there. Oops. That's okay. It's in a different. Sorry. Okay. Can't really see, but okay. So this is KDB. It's going to load up some things using a special branch of Blaze. Yes. Good. All right. We'll import some things. I'm going to fire up a Q process. KQ is this thing, and it just basically handles the state of the Q interpreter. Okay. So the repr needs a little bit of work. It's a little ugly. It's not that cool. So this is a Q string that just generates the two-column table. The thing in the square brackets is a keyed column, which is like an index in pandas, and this is a random ideas, so like basically like 1 to 0 to 100,000, and then some random data. Okay. So that just creates a variable. The way you assign things is t colon. So now I have a data frame actually right here. So that's kind of nice, right? So eval takes a Q expression and gives you back a Python thing. It's a data frame, okay? So we can also use Blaze tables, right? So these are the tables that we have inside of K, or Q. Inside of basically what are in memory. And kind is, yeah, you can ask me questions about that afterward, but some details there. So it's the data object like we saw with Matt's talk, right? And we have similar kind of things. And you can do all the things you can do with Blaze. Okay, so we have an in-memory table, right? And here's an example of into. I'm taking that result, which is basically the result of an expression commutation, and then I'm putting it into a data frame. Notice it keeps the grouper column in an index, and that's a data frame. So our result is a Blazy thing. It's an expression. You can put it into a list, and then this is just sort of, it gives you the same values. Okay, so that's good. Correct code. And then is there any overhead to basically sending this through Blaze as opposed to just computing directly in pandas? Not too much. Okay, we've got 3.5 milliseconds. Okay. And then there's a little thing that I wrote. This is sort of a cute little thing that lets you inspect the generated code. So that is the actual Q code that is generated by Blaze. There's probably extra parentheses that are not necessary. So definitely a work in progress there. Okay, so that's Q there, and how you drive it from Blaze. All right, I seem to have lost my presenter view. All right, so how does Q compare to other Blaze backends? Well, let's check it out. So I took the New York City taxi trip data set. It's about 16 gigs, and I partitioned it on KDB, which is you take the data set, you get all the unique values in a particular column, and then you shove the subset of columns on that particular value into a bunch of directories. Okay. And then for Blaze, we're using a combination of bcalls, multiprocessing, and pandas, and I'll show you some numbers. So the computation is very simple. It's just a group by on one of these three things and a sum on one of these two things. And then I took the Cartesian product of that and did the computation that way. I'm only going to be showing you medallion and passenger count on the grouper, and then on the sum, just I think trip time. Okay, just because all that data couldn't really fit in a plot on my slide. Okay, two machines. This machine, which is 8 cores and 16 gigs of RAM running OS X, and then 32 cores on some AWS instance, 250 gigs of RAM running Ubuntu. So one thing to sort of keep in mind is that if my machine were even less beefy than these 8 cores and 16 gigs, I'd still be able to run this computation because bcalls is a column store, and it reads from disk sort of transparently. Okay, so here's some numbers. So I may have to come around to see this. So on the beefy machine, you can see that strings, well, pretty much in all these sort of backends, the strings are, leave something to be desired. Okay, and you also see that by increasing the number of cores that you have is very effective for these kind of string computations. Whereas when I have a grouper that's an integer, which is passenger count, maybe not that big of a deal. Okay, we go from 2 to 10 seconds, 10 seconds to 2 seconds. Okay, so that's nice. I also did a comparison with pandas out of pandas single core running on the 32 gig machine, and so you can see that those are the results there. Pandas is very fast in memory, because you just suck that whole thing to memory and did computations. And then in the middle is my machine. So there's no 16 or 32 because cores on here. So are there any questions about this or anything that I've said so far?
Yeah. Sorry, is there anything I can learn from this?
Oh, that's a good question. So one thing to note is that strings need work.
Where are strings again?
So sorry. Medallion is a string column, and that's the grouping column. Oh,
so you mean that the left are higher than the right ones?
Right. So the medallion column is strings, passenger count is integers, and so the thing is that you get a pretty big benefit from using many cores when you're grouping by a string column.
Or by the integers. I mean, it's exactly the same. The ratio of blue to green is the same, roughly speaking, right?
Right. So I guess then the subjective time is much less when you're.
Right. Okay. Can I answer this question?
Sure.
So this data set is large. It's about 16 gigabytes. It wouldn't fit on a I could not do the right side of pandas. It's actually impossible. But I can do middle step. I can use bcalls and pandas and chunking on my 4 gigabyte laptop. And if I use one core, I'm only about, the blue line is maybe only twice as big as the pandas. Use about a factor of 2. I'm actually able to do the computation. Now when I actually start to use many cores, which I can do, I actually get to be faster than pandas. So they use multiprocessing. So it makes a previously impossible problem possible. It also allows me to use many cores. So I can use weak hardware, like my ancient 4 gigabyte memory laptop, to interact with this large data set. It also allows me to use a big 32 core machine effectively. I can use all 32 cores to make my problem. So if you don't want to call a cluster, just in a single box, that's like a decent beefy box, you can run it with it, use all the cores and stuff.
How did you get the data into
bcalls. So this is all sitting in a CSV that I had to do some munging on. Not too much munging, but we have ways that you can do that. Sorry, say that again. So that's with the split mechanism that Matt mentioned in the last. I'll show basically the guts of that to show you how it. Yeah, so it uses the multiprocessing API lets you construct a pool of workers, which then it has a map function, which will distribute it across your two different processes. Yeah. So I think that's because it's it's logical cores versus physical cores. Not that I know of. So I don't think so. Yeah. It's- Jeff is there just to. Did somebody else have their hand up? Yeah.
Which role does IO play in this case? If you want to read like 60 gigabytes from this,
So
how to have power IO in any case?
so bcalls is doing the work here. It lays the data out in chunks that fit in cache. It does some compression, then it reads them in.
Typically, like a hard disk HDDs, 200 megabytes per second.
This
5 times 16 is only 80 seconds. I don't really get the numbers right. What is the difference scaling?
Is the full data set 16 gigabytes, whereas here you're only looking at one or two columns that trip the value or the processor count?
yeah. So the full count. Yeah. No, this is not reading in the entire data set. Sorry, I haven't told you anything about bcalls, but it's a column store. So each column gets a directory, and so you can read a single column in at a time. Right. So one sort of example is like, say you do a selection, a Boolean selection, before you select out the subset of columns that you want. So you say like amount greater than something, and then you get two columns out after that. So Blaze will take the two column expression and put it in front before you do the subsetting. Okay. So in this case, yeah, we're only reading two columns and then two columns in each one. So you're not reading the entire data set into memory, which is kind of nice. Question on the end there? No? Okay. Cool. Let's see. So these are the KDB numbers, and I don't have a whole lot of information about how this works because it's totally proprietary. They have a free version of their interpreter, but I wanted to do the same computation in Q and see how it compared. This is a single core. It's pretty fast. It is also a column store, which I mentioned earlier, so it's not reading in the whole data set as well. Yeah. This is symbols, and the medallion is basically their it's a P attribute. It's basically like an index in a database. So the symbols are the medallion symbol grouper is faster than the hack license symbol grouper because medallion is sorted, and it knows some additional metadata about that column. Okay. So some questions that I had. Let's make sure I have enough time. Did I partition the data set correctly? I don't know. I'm sort of flying blind here. I learned Q, and then I was just sort of messing around, reading their documentation, seeing how things work. Maybe there's a better way to partition this data set. I basically have it in 365 dates. Okay, so every day of the year for 2013, there's a subset of the data. Am I doing the query optimally? In this case, I think I am because it's not very complicated, and there really is only one way to do it. Is it a fair comparison? So the way bcalls lays data out is different than KDB. Like I said, there's a directory of columns per value of the partition column, and KDB is using symbols, which it has more information about than strings in NumPy. Okay, so if you use strings in KDB, I suspect, I didn't run this benchmark, but I suspect that it would be much, much slower because it actually treats them as arrays. So you basically have a variable length array per row. Okay. So how does a Blaze version work? Because pandas is multiprocessing. Okay, it's pretty straightforward. Because is a column store, like I said, it uses numexpr, which is a nice sort of, it takes advantage of the CPU cache, and it does transparent reading from disk. Okay, so you can, similar to Blaze, you can look at a bcalls data set without reading the whole thing into memory. Pandas, as everybody knows, is fast. It's in memory, and then multiprocessing lets you compute each chunk in a separate process. So here's an example, and I can do this example live actually if I have enough time. Okay, so we get some Blaze, we load it up in a data object, we create a multiprocessing pool, group by the passenger count, the average trip time, compute the result. All we have to do is pass in the map function, map method of pool, and then it does it. Okay, so I timed this. It was about 5 seconds for that. And then these are the guts of how this works. Okay, this is like from inside of Blaze, and it's a pretty straightforward, I think, for what it's doing. Okay, it's taking a symbol. You're splitting that symbol into chunks that are of the size that you specified in the input. Partitions give you an index into the data set. We run map, okay? And then we get back a list of our results. We then concatenate those things. I think it actually uses pandas concat function. And then compute the aggregation expression that we got above on the intermediate result. Pretty straightforward, okay? And that's it. Just want to thank some people, Matt Rockland, Hugo Sheedy, Jeff Reback, and everyone at Continuum. So yeah, any questions?
Yeah, so I think we should ask before. How does it relate to map reduce in large data sets?
I don't know.
Do you have any numbers?
I don't. By MapReduce, you mean Hadoop? I don't know. I haven't done that benchmark. Compete on different sizes, is that what you said?
Well, I'm wondering to see who will go in which direction with the larger data sets, not only 16 gig, but
Sure.
talking
Terabytes, petabytes, that sort of thing. Yeah, I don't know. It'd be interesting to see, but yeah.
Maybe I just need some clearing on to that, how different
Sure.
compares to column store very fast. And so if you have something like that, you feed it SQL, it does the partition pruning for you, and it figures out what partitions are within the where clause, and pushes the where clause out to these different nodes. And I'm not sure in this ecosystem where that really is being done, because I don't know how functional read calls is, like what raw read calls will do. So if I have something that filters on something else that affects the partition, how is that working in Blaze?
Filters the partition what? I didn't hear you say.
Partition that has a filter that includes certain values of partition keys, so I can omit certain partitions entirely.
Selection natively. Yes, so it doesn't have any notion of an index or any metadata other than some data about the memory layout. No, it doesn't. There's some mailing list discussions of putting indices on, and I think Hugo here would really like that. So yeah, it is not. Yeah, talk to me afterward. Any other questions? Okay, thanks guys.